Hey, welcome back to your favorite Fundamentals of College math class. We're looking at events involving not and or, as well as some odds. So here's our here's our objectives. We'll start out with finding a probability that an event will not occur. So the probability of an event not occurring is 1 minus the probability that an event does occur. So, for example, and that the reason is because the sum of all the probabilities is 1 or 100% probability of each theoretical outcome. And your notation for probability of the event not occurring, if you want to use set notation, is probability of. Remember, if I would sometimes say not E on that. Probability of not E occurring is 1 minus the probability of E occurring. Sometimes this is best seen with an example. Let me give you one. The probability of not rolling a 3. So you've got a six-sided die. You could roll a 1, 2, 3, 4, 5, or 6. Right? Now, if we were just to do this thing straight up, we say, well, if I'm not rolling a 3, then my winners are a 1, a 2, a 4, a 5, or 6. So I have 5 winners out of 6 possible outcomes. Or you can just say probability of not rolling a 3 is 1 minus the probability of actually rolling a 3. So 1 minus what's the probability of rolling a 3? Well, I have a 1 in 6 chance that I actually roll a 3 because there's only the 1 3 out of 6. So you do the fraction work and you're like, oh, it's the same thing, 5 out of 6. Now, so why would you do it this way? Well, sometimes you have limited information. So the complement of an event is 1 minus the probability of the event, right? And maybe you only know the probability, or your data only entails the probability of the event occurring. So, in mathematics, you want to be able to have all the tools in your toolbox so that you can approach problems in different manners if needs be, based on the information. All right, if you're dealt one card from a standard 52 card deck, find the probability that you are not dealt a queen. Not dealt a queen would be 1 minus the probability that you are dealt a queen. Whoops, that's supposed to be a queen right there. So 1 minus the probability that you're dealt a queen. How many queens are there? 4 out of 52. So we got 52 out of 52 minus 4 out of 52. We got 48 out of 52. Let's see, both of those go into 4. So that's 12 out of 13 is the probability that we are not dealt a queen. Again, if you were to do this straight up, without using the formula, you say, how many winners are there? How many are not queens? All those are not queens. There's 44 right there. 44 right there. And then here's 4 more that are not queens. That's 48 total, right? 48 out of 52, or 12 out of 13. All right, probabilities with mutually exclusive events. So we're going to do or probabilities. So we're going to do a probability of one or the other. Mutually exclusive events are mutually exclusive when it's impossible for them to occur simultaneously. When it's impossible for them to occur simultaneously. So, like the first example I give is a mutually exclusive event. It's what's the probability if one card is randomly drawn? What's the probability of selecting a king or a queen? Probability of a king or a queen. So you want to say, is this mutually exclusive or not mutually exclusive? Mutually exclusive means I can't draw a card that is both a king and queen. There are no cards that are both. These are mutually exclusive. I'm either going to draw a king or I'm going to draw a queen. I can't draw a card that has both on it. Okay, so that's mutually exclusive. For example, sometimes it's easier to see one that's not mutually exclusive. An example we're going to do here in a minute is what's the probability of picking a numbered card or a spade? I can't draw these spades. Effort here. Or a spade. Well, there are cards that are both numbered and spade. See them all right here? So those are not mutually exclusive. Okay. Whereas the probability of drawing a king or a queen, that is mutually exclusive. Let me erase this. Do this problem here. Alright, so mutually exclusive is a situation there is no card that is both a king and a queen. So what's the probability of pulling a card that's a king or a queen? According to the formula, as long as they're mutually exclusive, sorry about that, when they're mutually exclusive, then it's the probability of A plus the probability of B, because there's no cards that are both. In other words, there's no double count. Okay, so probability of A or B occurring when it's mutually exclusive is probability of A occurring plus the probability of B occurring. So probability of the king or the queen, probability of the king plus probability of drawing a queen. How many kings are there? 4 out of 52. How many queens are there? 4 out of 52. So we've got 1 in 13 plus 1 in 13. We have a 2 in 13 is our probability of drawing a king or a queen, right? Again, we're only drawing one card. Either one's a winner. Now I know this kind of looks stupid. Why would I split this up when I know there's 8 winners out of 52 anyways, right? There's 8 out of 52 winners, so it ends up being 2 out of 13. Again, you want to understand the concept here, so that you can, because the questions will vary in how they ask things. Okay, and as we progress, we'll get more and more different situations. All right, so what if they are not mutually exclusive? So not mutually exclusive means they cannot both occur simultaneously, not at the same time. I'm going to come back to this right here. So probability of A or B is the probability of A plus the probability of B minus the probability of A and B. If you remember, that's the intersection right there. Okay. So here's the example. Probability of drawing a numbered card or a spade. This is not mutually exclusive because there are cards that are both numbered and spades. Okay. So, not mutually exclusive. Probability of A or B is probability of A plus the probability of B, but I got to subtract out probability of A and B. I got to subtract out the double count. So numbered, or I'm just going to put an S for spade. Okay, so what's the probability of drawing a numbered card? So I've got all these numbered cards right there. Okay. So we've got we got 36 of those numbered cards out of 52. That's the probability of pulling a numbered card. How many spades do I have? Here's all my spades right here. Okay, so we've got 13 those spades. So the probability of pulling a spade is 13 out of 52. Now notice we've double counted here because we've got some right in here that are both, right? Again, there are cards that are numbered and they're spade. So I got to subtract out that many cards that are both numbered and spade. So I got to subtract that out. So we got 36 plus 13 is 49 minus 9. I got 40 out of 52 or 20, 26, 10 out of 13, 10 out of 13. This is the probability of a numbered or a spade. I have a 10 and 13. Now let's just kind of check that. If you were to count all the cards that are numbered or spade without double counting, in other words, the number of winners, right? These are winners, these are winners, 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 and winners, 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 those three and that one right there. So I have 36, 37, 38, 39, 40. There's 40 out of 52 that are winners when I'm not double counting, right? That's why this works here, right? Inductively anyways. In a group of 25 baboons, 18 enjoy grooming their neighbors, 16 enjoy screeching wildly, 10 enjoy doing both. So I've got the groomers, I got the screechers. It looks like there's crossover. There's 10 that enjoy both. So if there's 18 that enjoy grooming altogether, that means I got 8 left that are only grooming, right? Because I got 18 total with the 10 crossover here. I got 16 that enjoy screeching. I've already accounted for 10, so 6. And in this whole thing, there's how many baboons? There's 25 baboons. So let's see, 18 plus 6, 24. So I got 1 left over that doesn't enjoy doing either, right? If one baboon is selected at random, find the probability that he enjoys grooming or screeching. Or, again, these are or. Probability of grooming or screeching. So the question is this mutually exclusive? And I say, well, that means I can't have, when I pick, I can't have one that likes both grooming and screeching. But the problem is there's crossover. So this is not mutually exclusive again because there are baboons that both screech and groom, enjoy grooming and screeching, right? So this is not mutually exclusive. I could go in, if all these baboons are in a hat, right? Pulling one out, I could pull one out that likes to groom and screech, right? They're not mutually exclusive. So I have probability of A or B is probability of A plus the probability of B minus the double count A and intersection B. So probability of grooming or screeching is probability of grooming plus probability of screeching minus probability of grooming and screeching. All right, so what's the probability of pulling somebody that enjoys grooming, right? So I have 18 winners out of 25 is the probability to just pull somebody that enjoys grooming. Probability of somebody screeching, I got 16 out of 25. You know, if you look at this just right here, you know this can't be the answer. In other words, you know this is not mutually exclusive because if I was to just have probability of A plus probability of B, like for a mutually exclusive event, this would be 34 out of 25. That's more than 100%. That's 1 point something, again, more than 100% that I pull out a groomer or a screecher. So there's no way that this is a mutually exclusive event because we've double counted. How many groomer and screechers are there? 10 out of 25, right? So we end up with, what is that, 34 minus 24 out of 25 is the probability I pull out somebody that enjoys grooming or screeching, right? In other words, all 24 here, there's only one left over. 24 out of 25 is a chance that I'm pulling out a baboon out of that hat that's a groomer or a screecher. All right, how about odds? Let's talk about odds for a minute. Odds in favor of an event E are found by taking the probability the event E will occur and dividing by the probability that E will not occur. Okay, so odds in favor, and here's one way that I like to think about it. I like to think about it, we have odds in favor as the probability of E over probability of not E. In other words, when we find the probability of E occurring, we have the number of winners over the outcomes, and probability of not occurring is like the number of losers, right? But they're because if I'm finding the probability out of the outcomes. So when I divide those, it just ends up being the number of winners, the ratio to the number of losers. That's how I think about it. So number of winners on top over number of losers, right? That's the odds in favor of an event. Odds against just flips that around as the number of losers to the number of winners. I think it's sometimes easier just to see it with an example here. So you roll a single six-sided die, find the odds in favor. So the odds, again, not the probability, odds in favor of rolling a 2. So that's number of winners to the dot dot, to the number of losers. So I have 1, 2, 3. Here's my sample space. How many winners are there? There's only one winner. It's a 2. Oops. One winner. Dot dot. So it's a 1, 2. And then how many losers are there? 1, 2, 3, 4, 5. So it's a 1 to 5. Or you can write it 1 to 5. That's your odds, right? So a lot of time when you buy like a raffle ticket, I think they're required by law to give you the odds. I don't think they give you the probability of winning. I think they give you the odds actually, right? So odds here, odds in favor of rolling a 2 are a 1 to 5. If they were to say what are the odds against rolling a 2, it's just the other way around. It's a 5 to 1. Now, if you're following um, the actual formula, you say, well, the probability of rolling a 2 is 1 out of 6. Probability of not rolling a 2 is 5 out of 6. So once I take 1 out of 6 divided by 5 out of 6, keep change flip on that, keep change flip if you remember your fractions, you just end up with number of winners to number of losers. All right, so 1 to 5. So again, odds in favor, winners, number of winners to number of losers. Odds against, number of losers to number, dot, dot, to number of winners. Just flips it around. Now, if you're given the odds, if the odds of an event are A to B, then we can go back to the probability. We could actually go back to the probability of an event, right? So if you think about that, if you're given the odds in favor, how'd they come up with this? Well, if the odds in favor are A to B, we know the equation is a probability of E or probability of not E. In other words, probability of E over 1 minus probability of E, A to B. So how do we solve for this probability of E right here? Well, let me let X be the probability of E. Okay, so I have A to B is X over 1 minus X. Again, I just replaced the probability of E with X. And I'm solving for X. I want to know the probability of E. So if I cross multiply this, I'm just showing you where this came from. And then I distribute this. Then I add the AX. Again, I'm solving for X. So A equals AX plus BX. I take an X out. And then I divide by that A plus B. So X is A over A plus B. In other words, the probability of an event occurring, if I know the odds, for example, we knew the odds in favor of rolling a 2. We knew it was 1 to 5. That's the A, and that's the B. So the probability of rolling a 2 is A over A plus B. In other words, 1 over 1 plus 5. 1, 6, 1 and 6. And we know that, of course. We're rolling a 2. Of course, it's 1 and 6. But what we're saying is if we know the odds are A to B, we can use this formula to go back to the probability. Okay, so for example, and that was just I was just giving you the why on that. That's why that is. The odds in favor of a particular horse winning a race are 2 to 5. So the odds in favor are 2 to 5. They just gave us the A and the B. So what's the probability the horse will win? Well, we know it's A over A plus B. In other words, 2 is our A, 5 is our B. So it's a 2 to 7. 2 and 7 is our probability that the horse will win the race. All right. Thanks so much for listening. Let me know if you have questions.